Okay, if you have repeated roots when you are looking at this characteristic polynomial, we're going to basically extend the idea we used in 5.1 with repeated roots. In 5.1 with repeated roots, the idea was if I already had c1 e to the 3x and I had a repeated root, I would have c2, I would add an x in e to the 3x. And with that, adding that x in, what that does is it makes it so that this and this piece of the solution are independent. So if there are repeated roots with multiplicity k, here we had multiplicity 2 in this example, for the characteristic equation of a r to the n, a r to the n minus 1, all the way on down for however many of our roots, then the part of the general solution to the differential equation here corresponding to the repeated roots will have the form. I'm not going to read it off because it's a mouthful, but the idea is here's the first case of repetition where you just have the constant, and just like before, we need to add something that will make sure that these are linearly independent. So we'll start by adding x, and if it was only multiplicity 2, we'd be done. But if you have a higher level of multiplicity, again, we're talking about multiplicity k, then you would just keep adding a higher power of x. And by adding a different power of x, that'll ensure that those pieces of that solution stay linearly independent. And then normally we probably wouldn't write it out this way. We would probably distribute that e to the rx. And we'd write it out something like this, where you have just c1 e to the rx, then c2x, then c3x squared, all the way on out for however many you have. So the general version is kind of hard to read and talk through. So let's say we took our characteristic polynomial, factored it, and we got this. Well, then we have three zeros. R equals 0 with a multiplicity of 3. R equals 1 with a multiplicity of 2. And then R equals negative 2 with a multiplicity of 1. So when we're going to write out the solution to this, we would have y equals, and then here would be my three pieces that come from that first 0. All of that is for r equals 0 multiplicity 3. I've got c1 e to the 0x plus c2x e to the 0x plus c3x squared e to the 0x. And now that first one's done. Then I'd go on to the next 0. But I don't need to keep going higher powers because this is a different exponential than all three of these were. Now, could you keep going? Yes, you could. You could go x to the third, e to the x to the fourth. The reason we don't generally is because one of the things we're going to need to do with these solutions eventually is do initial conditions. And it just gets, the more you introduce extraneous complication, the messier that gets. So as much as possible, we want to limit the powers of x that we have to have involved in these problems. So then we have our two pieces from that second root. And there was no multiplicity with this last root, so we just need to add that piece on. Now, the only thing I would say is with these e to the 0 x's, there's no need to write those. E to the 0 power is just going to be 1. So I would probably not write this way. I just did it for illustration purposes here. I would probably jump right from figuring out the roots to this more simplified solution. And so those 0 roots, it's just a little bit simpler when we're writing those out front. So you're not normally going to start with it already factored. We're going to start from scratch at these. So let's take a look at a couple of examples, and then you'll be off working on the first couple problems for homework. So we're going to look for a general solution to this fifth order differential equation. First thing is going to be to write the characteristic polynomial, which here would be 2r to the fifth plus 3r to the fourth minus 2r to the third equals 0. And then it's factoring time. Factor out the GCF. Which leaves us behind a quadratic. And then we'll factor that one more round from here, either doing your guess and check, dusting off your old factoring skills. But again, I do like these, the rest of the next couple chapters, at least, that we get through, whatever we get through this year, is kind of cool because it's a trip down memory lane of old math skills that you learned at one point and will all come together in these problems. So I have r equals 0 with multiplicity 3 r equals 1/2 with multiplicity 1, and r equals -2 with multiplicity 1. So when I'm writing that solution out, from the r equals 0 with multiplicity 3 part, I'd have c1 plus c2x plus c3x squared. Now technically, those are all multiplied by e to the 0x, but like I talked about in that first little mini example, I'm not going to bother writing the e to the 0x every time. My guess is you probably won't either, and that's just fine. Then I have my fourth constant with e to the 1/2 x, and my fifth constant with e to the -2x. Now the order of these doesn't matter. So if you had factored it in a different order and swapped the order of these, that's totally fine. The constants would get taken care of when we do the initial conditions. The only reason we even put the little subscripts is just to identify that they are not going to all be the same value necessarily. Okay, and then in this last example, we first write the characteristic polynomial. Now, when you have derivatives of y, those will give you r's in your equation in that characteristic polynomial. So the fourth derivative of r is going to give you r to the fourth. The second derivative, y double prime, is going to give you an r squared. But if you have just a y, not y prime, but just a y, all that contributes is the constant itself. So there's our characteristic polynomial, and we're going to have to do actually a couple layers of factoring because we have this r to the fourth and r squared. This can actually be written as r squared minus 9 times r squared minus 9. And then that can be factored a little bit further into r plus 3, r minus 3, and the same thing again. So we are actually going to have two roots that are both multiplicity 2. I've got r equals -3 with multiplicity 2 and r equals 3 with multiplicity 2. So when we go to write our solution then, it would be y equals c1 e to the -3x plus c2x times e to the -3x for my first root and the multiplicity of 2. And then we'll have c3 e to the 3x plus c4x e to the 3x. And we can get away doing that again because this exponential is different from this one. So we don't have to keep going. If they were all e to the -3x, if we had multiplicity 4, then we would have to keep going with the power on that one. But here we're fine as is.